So we've already seen that the slope of the secant line that connects 2 points, x f of x and x plus h f of x plus h, represents the average rate of change of the function from x to x plus h. And we've seen that the actual rate itself can be determined by the difference quotient, which is f of x plus h minus f of x over h, as long as h is not 0. Now, we know that h cannot equal 0 because that would cause the fraction to become undefined. But we can allow h to approach 0. In other words, we can take the limit which approaches 0. Now, when we allow h to approach 0, what we're doing is we're closing the distance between the 2 points. We're bringing them closer together. So if you look at this illustration here, you've got a curve. And let's say your initial distance, you're going from point P to Q1, and you see the secant line there. Well, let's slide Q1 a little closer to P, so now it's at Q2. Okay, and you see the secant line has changed, and the slope has changed. Now let's slide that to Q3. Pretend that's like, you know those children's toys where it's a bunch of wires with the beads on them and they move them around? Okay, kind of pretend that's what it is. P is fixed. That's a fixed bead, and we're moving the other one from position Q1 to Q2, now to Q3. The slope has changed, the distance between P and Q has become smaller, and then move it to Q4. And the distance has become even smaller between P and Q, H has become smaller, and our slope has changed as well. Imagine sliding that all the way until it touches P. Well, when it touches P, that secant line, that line between the P and the Q, suddenly goes from being a secant line to being a tangent line. A tangent line is a line that touches the curve at one point. A secant line is a line that goes through 2 points on a curve. A tangent line touches the curve at one point. So if we could bring the 2 points together where they're on top of each other, then instead of a secant line, we would have a tangent line. Now, when we let the distance between the 2 points approach 0, now we're not finding the average rate of change between the 2 points anymore, because essentially we're taking 2 points and merging them into one. Instead of an average rate of change, what we're going to have is we are going to have an instantaneous rate of change. So the secant line between 2 points is the average rate of change between the 2 points. The tangent line gives us the instantaneous rate of change. Think of the difference this way. It's like determining your average speed on a trip. That would be the secant line. You would, find the distance divided by time, or how far you went divided by time. And that would be your average speed over the entire trip. Instantaneous rate of change would be the exact speed you were traveling at a certain given point of time on the trip. So at 2 hours and 3 minutes into your trip, you look at your speedometer. The speed you're going at that point would be your instantaneous rate of change. So we have a definition here based on what we just talked about. The slope of the tangent line at x f of x is the limit as h approaches 0 of f of x plus h minus f of x over h of the difference quotient. So we're taking the limit as h approaches 0 of the difference quotient, and that is going to give us that instantaneous rate of change. Okay, a little bit more of a definition here. For a function y equals f of x, its derivative at x is the function f prime, little apostrophe mark is read as prime, so f prime, and it's defined by f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h, provided the limit exists. In other words, we're now giving this function where we take the difference quotient and we take the limit as it approaches 0, as h approaches 0, and we're giving it a new name, and that name is the derivative. And if f prime of x exists, then we say that the function f is differentiable. In other words, you are able to take a derivative. You are able to find this instantaneous rate of change. 3 steps to figuring out a derivative, at least for now. We're going to get to some shortcuts for that, but right now you need to understand how the long process works. The first thing you do is you write the difference quotient. So you take the difference quotient, we've done this before, you put the function into it. Then you simplify it as much as you can. You cancel the h's where you can, whatever you can cancel, and then you find the limit as h approaches 0. So let's try this example. For f of x equals x squared, find the derivative, find f prime of x, and then find the derivative at -3 and 4. So you're going to find the derivative first. You're going to do the limit as h approaches 0 of the difference quotient first, and then once you have that, it'll be like a little equation, and you're going to find out what that equals when x is -3 and when x is 4. Pause the recording, give this a try, and resume to check your answer. Okay, so here we're working out the difference quotient, putting the function in, and remember with that x plus h squared, you must square it out, you must FOIL it out. We were able to get rid of the x squares, and then we're able to cancel out the h's. So we have the limit as h approaches 0 of 2x plus h, and when we take h to 0, we get 2x. Now we're going to put -3 in for x and 4 and get those two values. So when x is -3, we get -6, and when x is 4, we get 8. Now try it with this equation. We've got x cubed. Same thing. Pause the recording, give it a try, and resume to check your answer. Okay, so here's the process. Cubing, a little bit more difficult, a little bit more involved. You do have to do x plus h times x plus h times x plus h, so there's a little more to it. But again, notice that the x cubes have canceled out. The h's, the h in the denominator cancels out, which allows us to take h to 0, and then putting in -1, we get 3, and putting in 1.5, we get 6.75. Okay, let's try another one. Use the results from examples 1 and 2 to find the derivative f of x equals x cubed plus x squared, and then calculate f prime of -2 and f prime of 4 and interpret. All right, so what you're going to do is you've really already done the derivative of x cubed, and you've already done the derivative of x squared. So you use that to find the derivative of the two added together. Pause the recording, give it a try, and resume to check your answer. Okay, so we know the derivative of x squared is 2x. By the way, kind of look at these things and see if you start to notice a pattern, because in the next section we're going to get into patterns and into ways of doing this that are going to be a lot shorter and easier. So I want you to pay attention to the patterns. So we know the derivative of x squared is 2x, and the derivative of x cubed is 3x squared. So we also know that you can add these two together to get the limit of the sum. So that means the derivative of x cubed plus x squared is 3x squared plus 2x. So putting in the two numbers, when x is -2, we get 8, and when x is 4, we get 56. Example, for f of x equals 3 over x, we are going to find the derivative, find the derivative when x is 2, and then find an equation for the line tangent to the curve at 2. Pause the recording, give these a try, and resume to check your answer. Okay, the derivative is a little more involved when you have a fraction. It makes it a little more difficult because it's a fraction. So it's going to be 3 over x plus h minus 3 over x over h. What we're going to do is we are going to give the top a common denominator. And so we do that and we combine them here. And the 3x's will cancel out, leaving us with -3h on top. And on the bottom we got x times x plus h. The h's from the very top and the very bottom will actually cancel, which makes us have -3 over x times x plus h, and then taking h to 0, we get -3 over x squared. For part B, we're going to put in 2 for x, and that gives us -3/4. Now, the equation for the line, well, x is 2, the slope is what we just found, which is -3/4, then you need the y value. Well, put in 2 to the original equation, and that gives you 3/2 for the y value. And then y equals mx plus b. What they're doing here is they're using the x, the y, and the m, and they're solving for b. This is a perfectly fine way to do it, or you could use point slope form first. And we end up with 3 halves equals negative 3 halves plus b, so b must be 3, which gives us the equation of y equals negative 3/4 x plus 3. Now, not every function is differentiable, and not every function is differentiable at every point in that function. That's probably a better way to say it. There are 3 things you need to watch out for, and the first thing you need to watch out for is a corner. So a function is not differentiable anywhere where there is a corner. So if you look at these graphs where you see the a, you cannot take a derivative there, and the reason for that is there are just way too many tangent lines. Think about how many lines would actually touch the curve in that one point. There's just way too many there. So where there is a corner, you cannot take a derivative. Concern is where you have a vertical tangent. Why can't you take a derivative there? Derivative is the slope of the tangent line. A vertical line has an undefined slope. So if your tangent line is vertical, the slope is undefined, therefore it has no derivative. Can't take a derivative there. And the final point where you can't take a derivative would be where there's a discontinuity. In this piecewise function here, you see the gap where x equals negative 2. It's not continuous there, so you cannot have you can't have a tangent line there. So it's not differentiable. So the 3 things you need to remember: you cannot take a derivative at a corner, you can't have a derivative where there's a vertical tangent, or where there's a discontinuity. All right, so check out this graph and decide whether it's differentiable. Now, when we talk about a function being differentiable, we mean over the entire thing. So if there is any problem with this function where you cannot take a derivative, you need to tell where and what the problem is. Pause the recording, give it a try, and resume to check your answer. Okay, it's not differentiable at x equals 6. This is the vertex. We know that the absolute value function is a v-shape, and it is a corner. So the function is not differentiable when x is 6. This is the summary of the section. You can just look over this, and this, like I said, summarizes everything we've just talked about. If you want to pause the recording and look over this, feel free, and then resume to continue. Here's some more of the summary. And the rest of the video is going to be additional practice problems. So if you will go through these, pause the recording, and then resume to check your answer, and proceed this way through the rest of the video.